Welcome AP 9.3. Now that we have learned how to figure out the shapes and the angles of a molecule, the question now is the molecule polar or nonpolar? So we need to use our knowledge from Chapter 8, extensively our knowledge of Chapter 8 when it has to do with polarity. So let's start from the beginning. We call that bond polarity. So is a bond polar or nonpolar? Is the unequal sharing of the electrons in between those two atoms. So as the difference in electronegativity increases, so basically the more different those two elements are, so does polarity. So when you're looking at something like, let's say, O versus F, okay? If you look at electron negativity, oxygen is about 3.5, fluorine 4.0, versus somebody that's like HF, when hydrogen's 2.1, fluorine's 4.0. This is more polar because the difference in electronegativity increases polarity. So this bond right here is more polar than OF, okay? Both bonds are polar, just one's more polar than the other. And that's going to determine, is the molecule still polar? So for a molecule consisting of more than two atoms, the dipole moment, and we do know how to draw those dipole moments, the dipole moment depends on the polarity of the individual bonds and the geometry. This is very key that you're understanding how we're going to be able to figure out if the molecule is polar or not. So when you have a dipole moment, we know it's the arrow with the little plus sign, and the arrow is basically telling me which atom is possessing the electrons. So the arrow is pointing to the atom that is more electronegative. The little plus sign means it's less electronegative. Okay? So to figure out if a molecule, very key, is polar, you have to first figure out the individual bonds. Are they polar or not? So are the individual bonds even polar to begin with? Because if they're non-polar, it's not going to be polar. You have to have at least one bond to be polar. And the geometry. And what's going to happen is it's this thing called dipole cancellation. Do the dipoles cancel out according to the geometry of the molecule? So depending on the shape, linear, bent, trigonal, planar, pyramidal, what type of shape is it producing, and will the dipoles cancel out? So for each bond in the molecule, excuse me, we have to consider bond dipole. The dipole moment due to only to those two atoms in the bond. So first, you have to have a polar bond somewhere. Okay, so that's usually your first question. So is there polar bonds in the structure? Because like I said, if you don't even have a polar bond, not anywhere in there, then the molecule is not even polar to begin with. You have to have polar in order to be considered a polar molecule. Consider the linear structure of CO2. So right here, CO2. The oxygens have lone pairs, but the carbon does not. So in this shape for CO2, this is a linear molecule. Your central atom has two double bonds on each side, so it has two electron regions. And I'm talking about carbon. Okay, and obviously the bond angle would be 180. Okay, just doing a little review. According to the double bonds, so right here, 3.5 for oxygen, carbon's 2.5. So the dipole moments, oxygens are more electronegative than the carbons. So what happens is these are not only polar covalent bonds, but your dipole moments, they are going away from the carbons. But both of them are going away from the carbon. So first, each bond, you got to have at least a polar bond. And we do. They're both polar. And because the polar bonds are identical, the polar dipoles, they equal each other in size also. And what they're trying to tell you right here, it's that difference. is the difference in electronegativity. Right here, 3.5, 2.5, that's a difference of 1.0. And over here, that's a difference of 1.0. They're not only identical, they're both going away from carbon, but they're both identical in size, 1.0, 1.0. Okay, if you do have one that's greater than the other, that will make a difference, so if they're not identical. So the plot of the molecule's electron density clearly shows that the individual bonds are polar, and that the overall dipole moment is what's going to happen is they're going to cancel out. So see, like these red regions right here, these are the oxygens, and they're very high electron density on the outside compared to the carbon that's in the center. The carbon is very low, and it's because those electrons, they are being pulled more towards the oxygen than the carbon. So the number of electronegativity values, it really makes a difference that you understand not only how to use them, how to calculate it, and to figure out if it's dipole or not. So bond dipoles and polar moments are vector quantities, and obviously that's a mathematical type of relationship. We look at both the magnitude and the direction. So remember, we've seen this word magnitude before. It's basically like when we did the magnitude of the charges, +1 versus +2, +3. So basically the size of the magnitude. Okay, how is it changing? And the direction, is it going toward the central atom, as in the dipole moment, or away from the central atom? Is the dipole moment going towards it or away from it? And CO2, as our example, the two bond dipoles, they're not only equal in magnitude, because they're both 1.0, but they're opposite in directions. But they're opposite as in both going away from carbon. Adding them in the same as adding two numbers that are equal in magnitude but opposite in sign, it's still 0. So if you have 1.0 versus a -1, then it equals not only in size but opposite in sign. So what happens is the bond dipoles, they're going to cancel out because they're both going away from the carbon. And because they both are equal in size and opposite in directions, the dipole moment will cancel. And this is very important. The molecule of CO2 has polar bonds, but the whole molecule, the dipoles will cancel each other out. And because the dipoles cancel each other out, the molecule in the end will be non-polar. Now why, one more time, you can have polar bonds, but if the dipole moments cancel each other out, if both dipoles are the same size and magnitude, opposite directions, the molecule in the end can be non-polar. So what this has to do with is something called dipole cancellation. So you're going to see the term in just a second. So because right here carbon is less electronegative, but both dipole moments, they are equal in magnitude. So equal in magnitude, but opposite in sign. They're both going away from the carbon. And because of that, it's called dipole cancellation, where all the bonds within the molecule cancel each other out. Now I know you're probably thinking, let's just say if. Let's say we had the oxygen, and let's say this mysterious, we'll call this carbon, but then maybe over here, maybe it's somebody else. Maybe it's like, trying to think of another one, less than carbon. Let's say it's, oh, you got me off track. But we're just going to call it X, okay, for time purposes. We know oxygen, more electronegative. But let's say this X compared to carbon is less electronegative. And I'm going to put the words than carbon. If that bond is polar, So this is polar covalent, this is polar covalent. We already know the electronegativity, the dipole moment's going away from carbon. But let's say this one is not going away from carbon, it's going towards the carbon. And in this case, you don't have opposite directions. You have the same directions. And because you have the same direction, that molecule is going to stay polar. So the molecule in the end will be polar because the dipoles don't cancel. And that is the explanation. I know you guys are always so keyed and zoned into, well, Rodriguez, how do I explain this? Like, what do I say? That literally is it. The dipoles do not cancel. And because they don't cancel each other out, the molecule will stay polar. Do not cancel out. Highlight it, highlight it, highlight it, okay? So one more time, because you know we're going to practice this to death. The dipole moments not only have to be the same size as an electronegativity difference, but opposite in directions. So if they both go in different directions, it's going to be nonpolar. But if both dipole moments, like this one right here with the O, C, and X, if dipole moments are the same size, but they go in the same direction, they're both going towards that oxygen, that doesn't cancel out. So the molecule will still stay polar in the end. The tricky part is, what if that central atom has lone pairs? Okay, so we're going to do various scenarios so you can see the difference. Okay, let's look at Mr. Water, the most famous molecule in the world, Mr. Water. And according to water, water has a bent shape. Oops, I don't know where it went. So water has a bent shape. Okay, stop moving on me, molecule. And with that bent shape, it's bent because, remember, oxygen has those two lone pairs. So it has a bent shape, and I apologize, I do not know why it keeps moving on me like that. Yeah, maybe it doesn't like it so close. There we go. Let's move it away. All right. Oxygen molecule has a bent shape because, remember, it has two bonding regions plus two non-bonding regions. And what would be the bond angle? Think, think, think. Before I shout out the answer, what would be the bond angle? You would put either 104.5 or you could put 105 degrees. Okay? Question is, these are polar. These are polar covalent. Both polar covalent, because I took the difference of it, 3.5, 2.1, so that's a difference about 1.4. So both bonds are polar. Polar covalent bonds. And both have the same magnitude. When you subtract 3.5 to 2.1, they're both 1.4. 1.4 on that side, 1.4 on this side, both same inside. So it's both same magnitude in difference of electronegativity. So now the question is, do the dipoles cancel out? Are the dipoles both going in the same direction, or are they going in opposite direction? Well, if you notice this one right here, it's going towards the oxygen, and this one over here is also going towards the oxygen. So they're both going to the oxygen, and they're both identical because they're both polar. So two bonds that are identical, they're polar, and the polars are equal in magnitude. Okay, we said that. Because the molecule is bent, here's the problem. See these guys on the top right there? They're going to stop. Lone pairs, they will stop the dipole moments. Oops. They will stop the dipole moments from canceling. They will not cancel out, okay? And you have to remember the whole point of a symbol. You have electrons on the left and the right, and the top and the bottom. Whether they're bonds or lone pairs, you always have electrons on all four sides when we draw it. The problem is you have two that are dipole moments, and they're both going towards that central atom. But then right here, you got lone pairs. And I'll put the other lone pair on the bottom. And because it's bent, that's the key part to this. It's not linear, it's bent. Because it's a bent molecule, these lone pairs, think of them, they're like stop signs. They're like, wait a minute, dipole, stop, hold up. Can't cancel out because we have a region up here that has no dipole moment. So these lone pairs up here, there is no dipole moment in lone pairs. There is none. So I always think of it when I describe this to students, it's like those lone pairs, they're stop signs, and hold up, can't cancel out because we have a region up here, a whole region on the very top of the molecule that will not cancel that dipole out. You would literally have to have a dipole coming in going this way also towards the oxygen to cancel it out. So in this case, because you do not have a dipole that's going to cancel it out, the molecule still stays polar. So the dipole moments do not directly oppose each other and do not cancel out because you have that region of lone pairs due to the lone pairs on the central atom. I don't care that the atoms on the outside have lone pairs or not. That doesn't matter to us. But because right here, that massive stop sign right there on that lone pair, they will not cancel out. As I said, you'd have to have another bond also coming in to make it cancel out, and we don't. So in that case, the molecule will still stay polar. It's not a zero dipole moment. They don't cancel out. So the molecule stays polar. So the definition of a polar molecule, AP asks you, why is it polar? Because all the dipole moments within the molecule do not cancel out. That literally is your explanation. Okay, same thing right here. Why is it nonpolar? The dipole moments do cancel out in the molecule. So before you ask me, where's the explanations? How do I explain this? I just told you right there, those two magical sentences. So out of all of the geometries from chapter 9.2, which of the following geometries will always produce nonpolar? So anytime you see linear, okay, because notice that carbon, no lone pairs. If you see trigonal planar, like BF3, I don't see any lone pairs. So what I'm going to do is I'm going to draw the dipole moments in here for you. So because oxygen's more electronegative, see how those dipoles equal in size but opposite directions. They will cancel. Fluorine, the most electronegative, every single one of these polar bonds, they're all going away for boron. All equal size and all going away from the boron. So they all cancel out. Now, this one right here, carbon tetrachloride. Carbon and hydrogen. What you get is carbon 2.5, hydrogen's 2.1. This is non-polar. And this is non-polar. And that's non-polar. And that's non-polar. That's the easiest molecule to figure out because you can't even be polar unless you have a polar bond. So there is not any polar covalent bonds. So it can't even be considered polar to begin with. You have to have at least one. Right here, xenon and fluorine, same thing. Right up there. Now this is expanded octet. And before you start looking at it like, wait a minute, doesn't it kind of look like water? It's got two lone pairs. And every single one of the dipoles are all doing the same thing. Well, the problem is, remember, this is expanded octet. And because this is square planar, two bonds on each side, lone pair on top and bottom, you have basically all directions, even the lone pairs is all direction, it will cancel out. So every direction is doing the same thing. Ladies and gentlemen, do not compare it to water because water has the two lone pairs. And remember, it's a bent shape. It's not linear. So that's why it's very key that you understand how to predict their shapes. Because if you said water's linear, then yes, it'll definitely be the nonpolar because linear is nonpolar. But because it's bent, then it is polar. Trigonal pyramidal, all of these dipole moments are all going away from the phosphorus, and phosphorus has no lone pairs. So that is nonpolar. And same thing with the sulfur. Every single one of those fluorines all have a dipole moment. So do you see some easy trends? If no lone pairs on central atom and all the dipoles go in the same direction, automatically it's nonpolar. Those should be the easiest ones to find. So if you have no lone pairs on central atom and all dipoles move either away or towards central atom. And all of these I put fluorine on it, but I could have put hydrogen, and then all the dipoles go towards the center. So if they all go to the center, it's still nonpolar. If they go away, it's still nonpolar. But beware of the lone pairs on the central atom. So if no lone pairs on central atom and all dipole movements either go away or towards the central atom, then they will always be nonpolar. The bond dipoles within the molecule are oriented in a way where they cancel those dipoles out. They should be the easiest ones to find, okay? So just beware if it has lone pairs. AP tip, okay? Cannot just say because of symmetry it is polar. You need to explicitly say the dipole moments cancel due to symmetry. So there you go. Even AP's telling you what to say. Okay? Whether you say it, ladies and gentlemen, because of this, all dipole bonds within the molecule cancel, don't cancel, it's the same thing. Okay? But a lot of times they want you to use geometry, as in the shape names, to figure it out. So right there, there's another key instance of what AP is trying to tell you to do. The following are examples of polar molecules. So let me show you how this works. Now here's another one that says linear, okay? But the problem is this. You need to remember that it needs to be equal in magnitude of the dipoles in order for it to be nonpolar. To be nonpolar. And you're going to see some instances where it probably looks like it's nonpolar, but it really is polar. So let's do this one, HCN. The problem is right here between C and H, that's nonpolar. You should always know all CH bonds always are nonpolar, covalent bonds. Don't waste your time with electronegativity. I see a CH bond, bam, no polar, nonpolar, nonpolar. But the problem is between C and N, nitrogen is more electronegative. So you actually have a dipole moment going away from that nitrogen. And because it's going away from the nitrogen, I don't have both dipoles doing the same thing. I have like a stop sign right here, stop. But on the carbon side, my 6 electrons right here, they're being pulled towards the nitrogen. So the molecule in the end is still going to be polar. Trigonal planar. Well, we just said trigonal planar right here. Trigonal planar is nonpolar. Why is this trigonal planar polar? Look at right there. Every single one of these has a dipole moment. They're all polar. But look right here, this oxygen. You have 2 sets of electrons, both being pulled away. It is not equal in magnitude of polarity. And that's what you tell AP. This is a polar molecule because not all bonds are not equal in magnitude of polarity. Right here, you have double the polarity that is in that double bond right there. You have more of a polar bond in that double bond than you do in these single bonds. So it's not equal in the magnitude of polarity. That's why it's polar. If that would have been a single bond and carbon had no lone pairs, then it would be nonpolar. Why is this as a tetrahedral? Why is this one polar? Well, remember, every CH, they're all nonpolars. So it looks like to be a nonpolar, but you do have one of the 4 regions that actually has a polar bond. That makes it not symmetrical. Symmetrical means equal on both sides. Okay, it's kind of like a coin. On one side it's the same, the other side it's the same. You just got a head versus tail, but it looks the same. The problem is the head and the tail are not the same. So you have two sides, and two sides are equal, but what's on those sides are not equal. So they don't want to hear about how it's symmetrical. They want to hear about how the dipoles cancel out in that symmetry. And unfortunately right there between that carbon and Cl, they do not cancel out. AP talking to you again. Beware of drawing. Drawn on paper, it looks like the dipole moments cancel, but the true molecular shape name, as in linear versus bent. Always, always, students get these two shapes very confused because of those lone pairs. If the true molecular shape does not cancel out the dipole, then you have a polar bond. So be very careful. You have to account both the geometry shape, aka the name, and the actual atoms in the bond dipole. So we have to take into account the shape name and what those dipoles are doing. But make sure you have at least a dipole bond. If there's something like carbon and the 4 hydrogens, you don't even have a bond. You have no polar bonds in that CH4. It's not even a possibility of being polar. Some other ones that are definitely polar, it's because of the lone pairs. So all of these geometries do not cancel out. So what happens is, it's because there's not only polarity, but there's lone pairs on that central atom that's going to make it not. So trigonal pyramidal has a set of lone pairs on the top. And seesaw has also 4 of them going one direction, but then you got a stop sign at the top. T-shape, now T-shape kind of looks like kind of a bent structure like water. Same thing, you got 3 bonds doing one thing, but you got a giant stop sign at the top. And then square pyramidal has a set of lone pairs also on that central atom. Okay, but planar, square planar, is nonpolar. So reminder on that square planar, look at that one right there. It has 4 bonds, but 2 of the lone pairs, one on top and bottom. Square pyramidal only has 1 lone pair on it. So in all of these cases, the dipole moment does not cancel out. You know how to draw. There's nothing wrong with your drawings. But now you just have to pay attention to what those bonds are doing. Are they polar or are they nonpolar? So let's use some examples and let's see if you can figure out. These examples give you a false sense that the dipoles cancel out. So we already know what water looks like, but when we draw water, we want to draw water in its true shape. We want to show that it's bent. And because it's bent, we have both bonds where the dipole moments, they are going towards the oxygen, but you have that stop sign right there at the very top that's stopping the molarities from canceling out. So in the following examples, the Lewis structure does not necessarily indicate the molecular geometry. So watch the AP YouTube video if you need additional help. So I'm going to work these out for you, but if you need some help, okay, get some help from that video, and it's on Teams. Bent structured, and let's do some review. What if I asked you about bond angle? So let's practice here. So the electron domain has 4 electron regions. And if it has 4 electron regions, this is called tetrahedral. But the molecular domain name is bent. Okay, so remember they can sometimes have different names between them. Bent shape, 104.5 degree angle. And what is the polarity? The polarity means it would be a polar molecule. And because the dipole moments in the molecules do not cancel out. If I take ammonia, and I'm not going to do the NOS, ladies and gentlemen, because we have pretty much NOSed beyond belief. This is what your structure would look like. And if I ask you to name the structure, well, the electron domain how many regions are around that central atom where you have 3 bonds and a lone pair. So that's 4 electron regions. So it's also tetrahedral. Okay. And then the molecular domain name, because you have 3 bonds and 1 non-bonding region, then it's called trigonal, but it's not flat. Remember, it looks like a pyramid, like a tripod. Then it's called pyramidal. Okay? Pyramidal. And the problem is between hydrogen and nitrogen, you do have polar bonds, and your polarities, they're all going to nitrogen. So it looks like it cancels out, but right there, there's your stop sign. Okay? So it does not cancel because of those lone pairs on the top. So in the end, still a polar molecule. What if I had CH2F2? So the problem is when you have 2 hydrogens, maybe put them on one on each side, and then you got a fluorine. Kind of looks like it would be nonpolar because, let's look at this. The fluorines would have lone pairs, but carbon does not. And don't even look at the hydrogens. Between carbon and fluorines, definitely polar. But what about between hydrogens and the carbons? Not polar. So don't draw dipole moments if it's not polar. So you have nonpolar, nonpolar. So it looks like, dipoles cancel. But there's a big but coming to this. Is it equal in magnitude of polarity? And what happens is you don't have equal magnitude of polarity. You have 2 bonds that are going away from each other, but then it's like if you put lone pairs on these, it cancels it out. I'm sorry, it stops the canceling out because you don't have every direction doing the same thing. Every direction has to do the same thing. And you have 2 locations right here where they're doing nothing. Okay, so it looks like it cancels. Top and bottom are doing the same. Left and right are doing the same, but it's kind of like water. You have those 2 lone pairs and it's stopping the cancellation. So unfortunately, this would still be polar in the end because not all directions are equal in magnitude. 2 directions are doing one thing, the other 2 directions are doing another. Okay? In the examples in 9.2, go back to the examples 9.2, number 1 and 2, and determine if they're polar or nonpolar. So back in our notes right over here, in 9.2, number 1 and 2. Okay, so with these ones right here, okay, we drew these. So I'm going to draw just a little sketch real quick. So we had ozone. I believe ozone looked like this. Okay, and had a set of lone pairs. It's oxygen, oxygen, and oxygen. So that means nonpolar, nonpolar, because the same electronegativity minus the same electronegativity. And right there, because you have the same electron negativity, you have these bonds, both non-polar covalent bonds. So the question becomes, is this molecule still polar? Is the polarities equal and equal distribution? And what happens over here on this side of it, it's not equal in distribution right there. So I know you're probably saying, but wait a minute, you don't even have a polar bond. You have 2 nonpolar bonds, not even polar. But the question is, though, are the polarities canceling out? If they were equal, if that would have been a single bond and a single bond, then it's definitely nonpolar. But you have twice the amount of electron density on one side. So in the end, you can have an actual molecule be nonpolar bonds, but in the end, the polarity makes it polar because of not equal distribution of electrons. You have twice as much electrons on one bond than you do on the other. For tin chloride, I believe when we drew this one, I think it looked like this structure right there for tin. Just trying to think real quick. Yeah, because it gained an electron. And I'm not going to draw the lone pairs on the oxygen, on the chlorines. But because of this, doesn't it look a little bit like trigonal pyramidal? In trigonal pyramidal, you're going to have all of these dipole moments all going towards the chlorine. But you got a big old stop sign right there on the top. So all your dipoles are going away from 10, but not on top. There's your stop sign. So in the end, it'll still be polar. For SeCl, question is, does it cancel? Does it look equal in electron distribution and equal in magnitude? And remember, these two lone pairs, doesn't it kind of look like water? For those lone pairs, they're going to gang up on that chlorine, and they're going to bend those bonds down. So because that is a bent shape, and all bents are polar. Those two electron pairs, even though these are polar bonds, the polarity is going to cancel, is not going to cancel out with those lone pairs on the top. So in the end, this is still going to be polar. Okay? For C double bond O, and I'll just draw one of them, it looks like it cancels, but does it? You have 3 polar bonds, but are they equal in distribution? Not on top, not that one right there. You have more electron density on top. So it's going to stay polar due to not equal distribution of electrons. And that's what you explain. It's not equal. They're all polar, and they're all the same polarity, but you don't have equal amounts on all 3 sides. Okay, so same thing for question number 2. Okay, and then you can try those ones out also. I believe most of these are going to be polar. I want to finish the rest of the ones in here, and you guys can determine on number 2, polar or not. So let me get back to where we were. Okay, so here we go. Let's predict polarity. So if I have SF6, and I'm going to draw it real quick. And it may look like this and this. Do the Lewis structure, predict the electron domain and the molecular geometries, and we're going to predict polar or not. Okay? Now, for time's sake, I'm not going to draw the lone pairs on the fluorine, but do know that all of these, they're all polar bonds. And because they're all polar bonds and all the polarities are going away from that sulfur. Sulfur doesn't have any lone pairs. This should make it very easy that all bond dipoles cancel out. So because all bond dipoles cancel out, in the end, it's going to be a nonpolar molecule. What would be the electron domain? Well, that's octahedral. And because there's no lone pairs, the molecular geometry name would also be the same because of no lone pairs. What if I had BrCl? Just 2 atoms, 2 halogens bonded together. Okay? For Br and Cl, Bromine's electron negativity, I know it's like 2 point something. I don't have this value, but I know chlorine is more electronegative. So because of that, we actually have a dipole moment going towards the chlorine. And because of that, chlorine being more electronegative, and that's it. You only have 2 atoms. So the shape is definitely linear. And because of that dipole moment not canceling out, they're only going in one direction. That molecule will still be polar in the end. For SO2, you're going to have sulfur in the middle, and then you'll have 2 oxygens. But the problem is the sulfur is still going to have lone pairs. And actually, if we do the NAS, I believe you're going to have double bonds. So let me erase this. Oops. Okay. And I believe actually it's going to look like this. So the sulfur will have the lone pair, and then the oxygens will have their lone pairs also. Now, it looks like they cancel out. So between the sulfur and oxygen, oxygen's more electronegative. So the polarities do come out of sulfur. They both go away. There's your stop sign right there at the top. And remember, it has a bent shape. So the bent shape would be the molecular geometry name. For time's sake, I'm just going to abbreviate like that. But the electron domain name, it's going to be trigonal planar. And trigonal planar because of the 3 regions around sulfur. But it's bent because it has 2 bonding and 1 non-bonding location. Okay? Because of that spot right there in the very top, it's not going to cancel out the dipoles. So we're still going to be polar. Silicone tetrachloride. Because silicone has 4 valence electrons, silicone's not going to have any lone pairs, but the chlorine would. And the chlorine has all those valence electrons. And I'm drawing all these dots and they're disappearing on me. That's freaky. Chlorine is more electronegative, so all of these dipoles, they go away. And because they go away, no lone pairs, all polar, all dipoles going away, it's going to be nonpolar. And the shape name for 4 bonds and no non-bonding would be tetrahedral for both names. What if you had BF3, so boron, and we know boron does not do lone pairs, so that is your structure, and fluorine with all his valence electrons. But where's the dipole going? Well, fluorine being the most electronegative, we know this is going to be polar. I don't even need any values. But because all dipole moments are going away from boron, and boron has no lone pairs, every direction's going out. And because this is trigonal planar, not every trigonal planar is nonpolar, but most of them are. And because right there, I don't have anything right there stopping me, so it's going to spread out and look like that instead, the true molecule. And this is going to make it nonpolar. Every polarity doing the same. Same thing with the 2 atom structure. Don't really have essential atoms, so we just have to see what's happening with that bond. And because between H and Cl that is polar, nothing is canceling it out. It's only got one direction, so it's going to stay polar. It's really easy when it's a 2 also. See you on the next one.